Hi guys, I'm Becky and I'm here to make chemistry your new favourite subject, or at least way less intimidating. Okay, so we're going to have a look today at atomic models, and this is one of the areas that no matter how many times I've marked it, it is always poorly answered. Now I've got my theories behind why. It's a little bit dry. We can't recreate the experiments that have been done to help us understand this, and some of it is going back to 1800 BC. Well, who cares about 1800 BC? Unless you're a history buff and you love it. Okay, so I completely understand why atomic models is poorly answered. But what I'm going to do today is to give you the fundamentals, just to give you the bits that you need to know. So stick with me for about 20 minutes and we'll master atomic models. I'm not going to go into any extras. I'm just going to give you the absolute necessities that you need to know. Okay, let's dive in. Okay, so here is roughly what we need to know. So going back to 400 BC, long time ago, yeah, even before me, we thought that atoms were indivisible objects. So we thought that they were, if you imagine like a marble or a ball bearing, something that we couldn't split, we couldn't make any smaller, was just this solid, small, indivisible object, and we stuck them together and made different things. Okay, and then over time scientists did various things, different experiments, etc. And when we learn something new, sometimes we have to change our models, we have to change our theories. And what happened between 400 BC and 1904 is that the electron was discovered. So we had to change our theories. So we need to know, why did we go from thinking about it was an indivisible object to what we call the plum pudding model, and I'll go into a bit more about that in a minute too. Now the next big jump is from the plum pudding model to the nuclear model. In this one we have to understand what experimentation was done, what the results were, and why the scientists changed the model again to the nuclear model. So from indivisible to plum, we just need to understand why they changed that model. From plum to nuclear, that's where we need to know the experimentation behind it. Jumping from nuclear to Bohr's model, it's a slight tweak. Again, this time we don't have to know about the nitty-gritty of what he did. We've just got to understand how he changed the model. And then we just got to know that now we know that protons and neutrons exist. We further adapted that model to the nuclear model that we discussed today. Okay, so we don't need to know every little step. The big one is between the plum pudding model to the nuclear model. Okay, so indivisible objects. What happened then is that J.J. Thomson, so I'll write his name down for you. So the scientist was J.J. Thomson. And we don't need to know what he was doing, what he was faffing about within his lab, what he did, but he discovered electrons. Okay. So he was doing whatever he was doing in his lab, he discovered electrons and then thought, well, hang on a minute, that means that atoms can't be these indivisible things because we've got electrons, and that's now two things. So what he then came up with, how he changed the model, he changed it to the plum pudding model. Now I don't quite like the name plum pudding model because, I'll be honest, I've no idea what a plum pudding is. Okay, so the way that I think about it, I almost imagine having a ball of cookie dough, because we know what that is, right? Ball of cookie dough, and that's the main part of your atom, and then taking some chocolate chips and just randomly sticking them in to your ball of cookie dough. And there we've got our new model of the atom. So the ball of cookie dough is like the positive charge, and then we've got these negatively charged electrons because J.J. Thomson's discovered them, so we've got to put them somewhere. So we're just randomly putting those within that ball, and now we've got our new model. Okay, so still quite solid, but is kind of divisible because we could take out the chocolate chips or the electrons. Okay, so that was the first step, and that happened because J.J. Thomson discovered electrons. The second step is the most trickiest because here we've got to know what Rutherford did and what he found out. So we've got to be able to evaluate his findings. Okay, so Rutherford is the scientist, Ernest Rutherford, and what he did is he fired alpha particles at gold atoms. So he took a sheet of singular layer of gold atoms and he fired alpha particles. Now alpha particles, if you put your physics hat on for a moment, alpha particles are made of 2 positive protons and 2 neutral neutrons. So overall an alpha particle has a positive charge. That'll be important in a minute or two. So Rutherford took this sheet of gold and he fired alpha particles at it. And what he found is that first of all, label where we've got the label A. So the first thing he found is that most of the alpha particles went straight through. Okay, so hang on a moment. If I've got that quite dense, that ball of cookie dough with my electrons dotted around in it, well, if I threw something at it, it's not going to go straight through it, is it? So we're going to need to change our model again, because if it's gone straight through, there must be some empty space in there. So we'll look at his findings first, and then we'll look at how he changed the model from that. In B, so at part B, what he discovered is that some of those alpha particles, so not many but some, were deflected. Okay, so what that must mean, hang on a minute, move myself out of the way. So what that must mean is if they were deflected, so if they've come at that gold sheet and then come out at a different angle, they've been deflected, then there must be some repulsion. So if those alpha particles have got a positive charge, that must mean that there's some positive charge in that structure of the atom. Okay, and then the final one up at C, he found that very few, and if you ever see numbers on this, it's 1 or 2 within hundreds of thousands that he fired, very few bounced straight back. Okay, so what did he conclude from this? So these were his findings, but okay, what did he decide? So the fact that most of them went straight through, he said, well then there must be empty space, because if there isn't, then they can't just fly straight through. The fact that some of them were deflected meant that there must be a positive area, should we say, for the moment. So there must be a positive bit within them. And that very few bounce back, it must be a small but dense, because it's hit it and bounced straight back, a small dense area. Okay, so these were his findings, and these are the ideas that he was thinking about. So that plum pudding, quite solid with the electrons dotted around in it, doesn't work anymore because most of them went straight through, so there must be empty space. So he came up with this model, and this was the first nuclear model, and we call it a nuclear model because it has a nucleus. Okay, so we can see now that we've got lots of empty space, so we can fire those alpha particles at it, and most of it, yeah, are just gonna whiz straight on through. Whoops, I've crashed into the nucleus, so that one would have bounced back. Yeah, but I can quite easily draw plenty of lines on here and go straight through. So we've got empty space. That explains why most of them went straight through. We've got a positive nucleus, but it's quite small in comparison to the size of the atom. So we've got a small dense area, and it's positively charged. So actually that big ball of positive, we've now condensed it right down. It's got to be small because not many of them bounce back. It has to be positive because the alpha particles are positively charged. And we've got to have majority empty space because most of them went straight through. So this is how we developed and how we changed to the first nuclear model of the atom. Okay. Then what came next is a scientist called Niels Bohr. So Bohr was the next scientist to change the model. So he's the scientist. And again, we don't need to know the nitty-gritty of what he was doing. He was faffing about in his lab, doing different experiments. And what he realised is that those electrons, they do orbit around the outside. However, rather than, this is the kind of diagram, if you just Google atom, this is what comes up, isn't it? You see those sort of oval-shaped orbitals. But what he realised is that actually those electrons sit at specific distances from the nucleus. So that's jumping into sort of the 288 rule that we know today. Okay, so all that Bohr did was put the electrons at specific distances from the nucleus. Okay, so if we just pop back to our timeline at the start, indivisible objects. First one is that J.J. Thomson discovered electrons, so we needed to change that model. So we went to the plum pudding model. Positive dough, electrons dotted inside of it. Ernest Rutherford then did his gold leaf or his alpha scattering experiment. We need to know what he did and what he deduced from that. So he then changed it to the nuclear model, so a small, dense, positive nucleus, electrons orbiting around the outside. And then on to Bohr's model. Again, don't need to know the ins and outs of what he did, but Bohr put the electrons at specific distances from the nucleus, thinking about now our 288 rule. And then again, we don't need to know any more from that, but you can see then that between Bohr's model and where we are now, or at the timeline in 1932, neutrons and protons had been discovered at that point, and so that nucleus became built up of the protons and the neutrons. When we were looking at Bohr's model, we just knew that it was positively charged. Now we know that it's further divided into those neutrons and protons. Okay, so let's have a look then at some questions. Let's look at how it's going to be examined. So here are some lower level questions to start with. So these would be what you would find early on in a paper. So as I've said in previous videos, they are low demand because you check the right box or you put the right singular answer in. However, you still to have that knowledge, you still need to know who did what, who discovered which bit, what particle did they use, etc. Okay, so if we have a look at the first one, atoms were first thought to be tiny spheres that could not be divided. which particle was discovered to change that model. So how did we go from tiny spheres into the plum pudding? We discovered electrons. And with questions like this, just be very careful that it says tick one box. If you tick the incorrect box, please make sure that you make it really obvious. Yeah, if I ticked neutrons first, make sure it's really obvious that I no longer want that. In an ideal world, you'll do it in pencil and be able to rub it out. Not going to happen, is it? You're going to do it in your pen. Just make it really obvious that you don't want that one, because if you then tick a second box, you will negate your mark, you'll lose your mark. So just be careful how many boxes it wants, make sure you only tick the right amount. Part B, the diagram shows another model of the atom. What is the name of this model? So you're going to see in another question little sort of diagrams of the models. It's worth just trying to lock in what they look like so you can identify them. So here we've got the plum pudding. Okay. Scientists fired gold atoms. Some of the particles were scattered, and this led to a different model. What type of particle did he fire? So he fired alpha particles. So as I say, you've still got to have that knowledge. And part D, which scientist first suggested that electrons orbit the nucleus at specific distances? That was Bohr. Okay, so here are the little diagrams. So these are your diagrams of your different models. So the model that represents the plum pudding model is B. So we've got that overall positive charge, those negative electrons dotted within it. Which model resulted from Chadwick's experimental work? That was, lost my pen, that was D. Okay, and then the final part is a little bit of atomic structure. Okay, but obviously we know what the atom looks like today from these scientists and their experimentations. So atoms of the same element have the same atomic number because they have the same number of protons. Remember, it's our protons that dictates which element we have. Atoms of the same element can have a different mass number because they have different number of neutrons. Comes from our isotopes. And atoms have no overall charge because they have the same number of positive protons and negative electrons, and therefore those charges balance out. Okay, so this, although it is a tick box, this is a higher level question because here you are having to sort of analyse his results and say what the findings were. So this one, we've got the alpha particle scattering. You see there we've got the piece of gold foil, we've got the alpha beam being fired at it, and we've got the 3 different variations that he found. Most of them straight through, not deflected. Some were deflected, as we've got the arrow that's bouncing straight back. So the 2 conclusions that were made from this experiment is that the atoms must have a positively charged nucleus, because if we're firing positive alpha particles at it and some of them were deflected, then we must be coming next to the same charge and we get that repulsion. And the second one is that the mass is concentrated in the nucleus. It's concentrated in that small space because only very few bounce back. Okay, neutrons exist within the nucleus, yes they do, but we didn't know about neutrons at that time. Okay, and then finally, this is what most questions are like. Most of them ask you to describe the difference between the nuclear model. So the nuclear model is the nucleus with electrons around the outside, and the plum pudding model, which is more of our solid model. Okay, now questions like this, a little bit of an exam tip here, is where it says describe 3 other differences between the nuclear model. Okay, so because it says nuclear first, so the nuclear model and the plum pudding, whatever you write down, if you just write it is mostly empty space, as an examiner we are presuming that by it you mean the nuclear model, because that's the one that's listed first. So if you wanted to say it kind of the other way around, if you said its model is solid, referring to plum pudding, then there you wouldn't get the mark, because it is solid, the first one in the sentence is nuclear. So as an examiner, I would be thinking that you mean that the nuclear model is solid, therefore you wouldn't gain the mark. However, if you said on the line, the plum pudding model is more solid, you're in, because you've stated which one you're talking about. Okay, so just be careful, and that's across the board. Yeah, any area of science, whatever comes first within the question, if you write it is da-da-da, we're going to presume that you're talking about the first one listed. It's called the list rule when examiners mark it, so just be careful of that you're talking about it. Okay, so we've got there that the plum pudding model did not have a nucleus, so we need to talk about other differences, 3 other differences. So we can say it is mostly empty space because the nuclear model is mostly empty space. Okay, the alternative, the other way to say that would be that the plum pudding model is solid. Okay, the second thing we could say is that its positive charge is in the nucleus. Okay, again, reverse of that, you could say the plum pudding model, the ball is the positive charge. So if you're saying it the other way, just make sure you say the plum pudding model. Another thing we could say is that the mass is concentrated in the nucleus, or in the centre. Okay, and a reverse of that, talking about the plum pudding model, is that the plum pudding model, the mass is spread out. And a further one that you could have is that in the nuclear model, the electrons in the nucleus are separate, whereas in the plum pudding model, it's combined within that structure. Okay, and then the final question, Niels Bohr adapted this model. So we've got to the nuclear model now by what Ernest Rutherford did. Niels Bohr slightly adapted that nuclear model, described the change that Bohr made to the model. So he changed that the electrons orbit the nucleus. So we'll mark number 1. And he said that they orbit the nucleus at specific distances. Okay, so he brought us into the sort of 288 rule that we know today. Okay then guys, hope you found that helpful and a little less boring. So I'm hoping to see loads of smashed out answers for this area now. Okay then guys, I'll see you next time.